Swayam Prabha. Digital India. Educated India.
Welcome to this lecture number 14 on unsteady radial flow in confined and unconfined aquifers. And here in this lecture, in the previous lecture we discussed on unsteady flow into the wells, and in this lecture we will be moving on to confined as well as unconfined aquifers, and of course the flow is radial and it is unsteady. And here in the this previous lecture, so there was this unsteady flow equation which was solved by two methods, that is two graphical methods. One is the time drawdown method, as well as the one is, I am sorry, this the unsteady radial flow in confined aquifers. So, in the previous lecture we had this we discussed the solution of Thay's equation by two graphical methods, namely one by type curves and two by Cooper-Jacob approximation. And in this lecture we will discuss another method for the solution of the Thay's equation, which is used in the unsteady radial flow in confined aquifers, and that method is the another method for solution of Thay's equation by this developed by Chow. So, which is this method, that is why this method is known as the Chow's method. Chow's method of solution. So, here what is done is, so in a pumping test, so a curve is plotted and a semi-logarithmic plot, the observed data is plotted on a semi-log plot. That means the drawdown axis is on a linear this one scale, and the time axis is on a logarithmic scale. And here, so this is on the plotted curve. So, arbitrary points are chosen and their coordinates, that is the time coordinate t as well as the drawdown s. So, they are determined, just like say here. So, this is drawdown s, and then this is log of time t. and here. So, this is a tangent to the curve at a chosen point and determine the drawdown difference delta S in feet per log cycle of time. So, here actually say that is say suppose this is the, say these are the points, suppose we are getting. So, what should be done is, so this is the log t axis, and here say this is maybe this is 1, this is 0, this is 1, this is 2, 3 and 4 and so on. So, here say 2 points are chosen on this plot such that the difference in log t is equal to 1, and so that the corresponding difference in this, say for example, these are the 2 points, and here. So, this is, so this difference is 1, where, and this is, so this difference is delta S, that is the change in drawdown per that is one scale difference of the log value of time, and here. So, this Fu is a parameter which is a function of this well function u, well function parameter. So, this is equal to S the drawdown divided by delta S. So, drawdown divided by delta S, this is delta S, and then the original value of this is S here. So, this is the value S, the drawdown, the typical value S, and then so this is delta S. So, this F by delta S by delta S is denoted as Fu. Then what is done is the corresponding values of W and U are obtained from the figure. So, this figure is so here we have this Fu which is S by delta S, and then here we have this WU, that is the well function. So, here, so the corresponding values of W and U are obtained from this figure. So, here this in this, so this Fu, so this is also on logarithmic scale. So, this is log scale, and W is also on log scale. So, this is a log plot of Fu versus Wu, and here. So, this curve will have a shape of like this. So, initially the slope will be flat, and eventually the slope increases. So, this will be the type of the curve, and so these along this the curve. So, the values of the well function u are plotted, are denoted, and here. So, typically, so this is say this Fu axis may start with 10 to the power minus 1, and then this is 1, this is our 0.1, and then this is 1, and then so this is 10, and similarly here this is so this is 10 to the power minus 2, and then this is 10 to the power minus 1, and then this is 10 to the power 0, or there is 1, and then so here this is 10, and then so on. So basically both these scales are on this is a log plot, and here typically the values of u, so they start with say here at the top it may start with say point, this u is equal to point 0001, that is 10 to the power minus 4, and so here you will get says 10 to the u is equal to, here u is equal to 0.001, and somewhere here you will get u is equal to 0.01, and here this is u is equal to 0.1, and then so here where the slope changes, so rough in this u is 1, and here this all the way it is close to this one, so this u is equal to say 3. So typically this is how the value of the well function u changes, and then so using this, so here what is done is, so the using this equation, that is Fu is equal to S by delta S. So this one I would so this Fu is equal to S by delta L, let us denote this equation as 1, and then so here the corresponding values of Wu and U are obtained from the figure, that is this figure. Okay, so this is the relationship between Fu and Wu. So this is the Chow's relationship between Fu, Wu and U, the well function U. So this U is the well function. And so here what is done is, the formation constants, that is the transmissivity, the aquifer formation constant with transmissivity T is obtained by so the equation that is the typical drawdown is equal to q divided by 4 pi t, and into this W. So here this W is known, S is known, Q is known, and so therefore T can be determined. So that is T, the transmissivity T is equal to Q divided by 4 pi S into W. Okay, and so this is the first this one, the and then next the the storativity S is obtained by the equation S is obtained by, so this is a storativity S obtained by the equation that is R square by T is equal to 4T by S that is the well function equation. So, we know that well function is equal to R square S divided by 4T into T. So, by this expression we get that is so this is the well function equation. From this the storativity S is equal to, that is U into 4 pi and U into 4 transmissivity T into time since pumping divided by R square. So, like this, using this Chow's relationship between this Fu and Wu, so we can determine the formation constants of the aquifer. Okay. And so, now we will move on to the unsteady radial flow in unconfined aquifers. So, this Chow's method is the third method by which we can solve the Theiss equation, and now we will move on to unsteady radial flow in unconfined aquifers. So far we have seen the confined aquifer wherein the it is under pressure and wherein the things are somewhat more straightforward, I should say, as compared to the unconfined condition. And here in this case, so this there will be it represents three types of behaviors. Say suppose we plot the drawdown S versus time t on a log scale. So, this is a log of S, the drawdown, and then the log of t, the time since the pumping. So, here, so it indicates three different kinds of nature. So, the first one is this segment 1, wherein the slope is quite steep. So, this here we can denote, so this as the segment 1, wherein the slope is, you can say, it is relatively steep. Then, so this is what happens is, so the as the time increases, the as time further increases, the drawdown will just marginally increase, and so this one here we can denote this as segment 2 or stage 2. Segment 1 having a relatively steep slope, then segment 2 having a relatively flat slope, then again in the third this one. So, this is here you can say, so this is segment 3. So, here what happens is, so the gravity drainage, and obviously in this unconfined aquifers, so the drainage is by gravity, and this gravity drainage is not immediate, and obviously that is why it constitutes an unsteady flow condition. And so the water flow towards well in unconfined aquifers is characterized by slow drainage of interstices. So, basically and water flow, or rather groundwater flow towards a well is towards a well in an unconfined aquifer shows a slow drainage through the interstices or the pores. That is why initially what happens is, when the pumping starts, so then this drawdown increases, and this is drawdown increases relatively steeply in this first segment, and then once, so this it has increased. So, then what happens is, so the here, so the that is the cone of depression. So, here there will be compaction of the aquifer as well as expansion of the water as pressure is reduced from pumping. So, initially there is a compaction of aquifer, and expansion of water. As pressure is, as there is a reduction in pressure due to pumping. So, this the first segment, that is so the first segment having the steep slope or steep drawdown. So, here what happens is, so this will continue for a very short while, and here, so the drawdown reacts similar to a unconfined aquifer. So, that means, so here this is the gravity here in this region, it more or less behaves like a confined or artesian aquifer or pressure aquifer, and afterwards what happens is, so this gravity drainage starts. So, this is basically, here you can say this is segment 1, here you can say this is analogous to, so here this segment 1 is analogous to say confined aquifer or artesian aquifer or pressure aquifer, confined flow. Next, here this segment 2, so here, so this is slow gravity flow in the segment 2, and here, so this is because of the expansion of the cone of depression. So, in the segment 2, there is expansion of the cone of depression. Here you can say there is a gradual expansion of the cone of depression, and hence slow gravity drainage. And so this continues, and next is in the third segment, in segment 3, so the time drawdown curve almost resembles non-equilibrium type curves. That is unsteady groundwater flow curves. So, and therefore, so there are 3 distinct segments. Segment 1 having analogous to confined flow, segment 2 having slow gravity flow, and then in segment 3, so there is, this is unsteady flow again, which is maybe again somewhat like segment 1, and then again the slow flattens like that. So, here, so therefore, in such case, so this the relationship between the drawdown and the discharge was drawdown S and discharge Q. was developed for a fully penetrating well in an unconfined aquifer by Newman in 1975 as S is equal to, the drawdown S is equal to Q divided by 4 pi T, the discharge divided by 4 pi into transmissivity, and here, so this is a well function of 3 parameters, that is UA, UY, comma eta, and here where this UA, so each of them represent one segment, UA is equal to R square into storeativity divided by TT. So, in case of the unsteady flow in a confined aquifer, it was the well function U is equal to R square S by 4 TT, whereas in this case, so this UA is R square S divided by simply T, the transmissivity, multiplied by the time since the beginning of pumping. And here, so this is so this is this W of UA, UY, and so this is the note, this is denoted as the unconfined well function. UA is given by R square S by 4 TT, and then UY is given by R square SY divided by TT, and this is applicable for higher T values, higher values of time. So, it represents segment 3, and this eta. So, eta is given by R square Kz divided by B square Kr. So, here this Kz is the vertical hydraulic conductivity, and Kr is the horizontal hydraulic conductivity. And obviously, R is the radius, and then B is the, that is the unconfined aquifer thickness. So, using these 3 parameters, that is the unconfined well function is more complicated as compared to the well function in case of a confined aquifer, wherein there is only one parameter, that is well function parameter, that is u is equal to 4 square, that is r square s by 4 t t, whereas in this case it is a function of 3 parameters, that is u a, u y as well as eta. And here the theoretical curves for this u a and u y as well as eta are given by this Newman's curves. So, the Newman's curves for unconfined well function. That is W u a comma u y comma eta. So, here in this Newman's curves we have along the vertical axis, of course, here also this is a log plot, and so here we have, so this is a W u a u y and eta. And here it starts with say 0.01, then 0.1, this is 1, 10, 100. So, this is the unconfined well function which is plotted along the, that is the vertical axis, and then here we have, that is 1 by u y along the horizontal axis. So, it starts with say 10 to the power minus 5, then 10 to the power minus 4, 10 to the power minus 3, 10 to the power minus 2, 10 to the power minus 1, then this is 1, then it further extends. So, this is 10, then this is 10 square or 100, and then this is 10 cube or 1000. And here what happens is, so somewhere between this 10 to the power minus 1 and 1, so here this is the curve, it goes up to, so this is 1, and then similarly somewhere between 10 to the power minus 5 and 10 to the power minus 4, and so this curve goes up to say a little over 10. And here, so these are the, so this is the, here actually let me, so this is the Thay's curve for 1 by u a, and this is the Thay's curve for 1 by u y. and in between we have, okay, let me use a different color, this one, that is so this is 7 and so this is 2 . This is 2 and so here this is 0.2 . And next here this is 0.001. So this is 0.2 and then this is 0.001. So these are all the, so this is the eta values. So this is eta is equal to 7, eta is equal to 2, eta is equal to 0.2 and then this eta. So this is eta is equal to 0.01. So this is how the theoretical curves for the you can say this is the Newman's theoretical curves. For unconfined well function. So like this, here we will get it is more complicated as compared to the unconfined flow, radial flow in a confined, I am sorry, unsteady radial flow in a confined aquifer, wherein, so it is there is it is only there is a well function parameter, that is u is equal to r square s divided by 4t into t, whereas in this case, so there are 3 parameters. One is ua, which is given by r square s by tt representing the first segment, uy which is equal to r square sy divided by tt, which is applicable for the higher values of t representing the third segment, and then eta, so which is a ratio of r square by b square, that is the distance from the well axis, the radial distance from the well axis, square of that divided by the square of the unconfined aquifer thickness. Of course, that is itself is a variable, and multiplied by the ratio of the vertical hydraulic conductivity and the horizontal hydraulic conductivity. So like this, so the in this the unsteady radial flow in an unconfined aquifer is even though it is the unconfined aquifer is the one which is which is the first aquifer as we encounter when we go from the ground surface, but here, so because it is at the top and then so there it is more it is subjected to more fluctuations because of the natural as well as natural groundwater recharge, and it is the reason, and many times if it is a this one in some cases where the even evaporation may also play a predominant role at if the okay, if there is a tropical desert kind of situations like oasis or anything. So therefore, so it represents more intensive. So unlike the unsteady radial flow in confined aquifers, so this unsteady flow in unconfined aquifers represents more this one. So now with this we will go to, we will just I will briefly, that is start with that that is leaky aquifers. So, that is the unsteady flow and here. So, these leaky aquifers, so they may have either a bottom confining layer which may be leaky, or they may have a top confining layer which may be leaky, or even both the top layer as well as bottom layer may be leaky. And of course, one, if the bottom layer is having more perforations, or in that case, so what happens is there will be the aquifer will be losing water, whereas on the other hand, if the top confining layer is more leaky as compared to the bottom confining layer, so then in that case this leaky aquifer may gain in terms of groundwater. So, therefore, so it represents an entirely different this one, and here, so this is the Walton presented the theoretical curves for leaky aquifer. So, this is so this leaky aquifer may have say with single leaky confining, or rather confining means say semi confining layer, say leaky, that means semi confining layer, or with double semi confining layers. So, double means this confining layer may be at the top or as well as at the bottom. So, in this case, the theoretical curves were developed by Walton in 19 so theoretical curves for leaky aquifer. So, this is the Walton's theoretical curves for leaky aquifer. So, they were developed in the year 1960, and here, so similar to the well function for the unconfined aquifer, here we have a well function for the leaky aquifer, and that is denoted by W u comma R by B. And here we have this is 1 by u, and of course both are on this one, and here this the axis, the W u comma R by B. So, that is this is denoted as leaky well function. So, this is the so in case of confined aquifer, it is W, there is a well function, that is W, whereas in case of unconfined aquifer we have unconfined well function. So, that is W u a u y comma eta, whereas in this case the leaky aquifer. So, this is somewhere in between, a confined aquifer and an unconfined aquifer. So, here there are two parameters, the first parameter is u and the second parameter is r by b. And so, this is the leaky well function, that is w u comma r by b, and it is the theoretical Walton's theoretical curve. So, it is here the w u axis will start at say 0.01 and then this is 0.1. So, this is 1 and then 10, and then similarly here the 1 by u axis will start at 0.1, 1, 10, 100, 1000 and 10,000 or say 10 to the power 4. And here, so this Thay's curve is the one which starts somewhere in between, that is 0.1, okay. That is 0.1 and 1, and so it starts here. So, this is the Thay's curve. So, here this is r by b is equal to 0.05 and this is the Thay's curve, and here for from the same point so this is r by b is equal to 2.5, and in between so there are different this one. So, this is there is r by b is equal to 1, and here this is r by b is equal to 0.1. So, like that, so this in this case the drawdown, which is a function of r and t, is given by q divided by 4 pi t into the leaky well function, that is w of u comma r by b. And again, so here this u is the same as the confined well function parameter, that is r square s divided by 4 t t, okay, and this and r by b is equal to r into under square root k dash divided by k b b dash. Okay, and this u is the same as the one, and here this is here this b dash is the equitard thickness. So, this is the k dash is the hydraulic conductivity of equitard, or leaky aquifer. So, that is leaky aquifer, and b dash is the thickness of equitard, that means leaky aquifer, and k and b are the for the regular aquifer. Okay, we will stop here and we will continue in the next lecture we will move on to the further topics in this well hydraulics. Thank you.